One of the great pleasures of working with complex functions is just the sheer beauty of what they do. And, um, and so this is one of the big attractions that people have for the study of complex variables. So what we're going to do is look on a complex function as a mapping. And I've picked one out that is a very important one. It's a fraction. The top is z minus I, the bottom is z plus I. Now this is a fractional linear transformation. It's in that form as a fraction az plus b on the top, bottom cz plus d, the determinant's non-zero. So this is a very important class of functions as far as understanding what's going on in complex geometry. The first thing you ask is about 0, 1, and infinity. You ask about the image, and you ask about the where those come in the domain. So let's just take a quick look. It's going to be a little bit of a surprise because, first of all, when z is 0, then w is minus 1. So if you look at the function, you've got z is 0, you've got minus I over I, so that's just minus 1. And 1 goes to, we'll come back to 1 because it's more interesting to see what gets sent to 1. Infinity gets sent to 1. I'm treating infinity as if it's something that happens in the under stereographic projection on the Riemann sphere, and so as z goes to infinity, this approaches 1. So there it is. We're in good shape that way. Okay, and the other thing that's interesting is I gets sent to 0. So again, that's just plug in. So when I at the top is 0. Okay. Minus I is a problem. Don't cry your eyes out about it. Okay. So the way that we're going to analyze this is look at, you got to look at something special because the domain is the complex plane and the range is, wait, hold it. The graph of the function is in 4 space. You get 2 in the 2 dimensions in the domain, 4 dimensions in the range. So we're not going to just have a nice graph. We're going to have to look at things. So we look at real parts, we look at imaginary parts, we look at the axes, and so that's what we're going to do. So we're going to start with the y-axis. On the y-axis, let's let the parameter be t, so the coordinates are it. So what the function does is it takes you to this thing here. It's still a fraction. Top is it minus I, bottom is it plus I. Oh, there's a common factor of I, so this is a real number. So that's the most important thing that we can say about it, and so there it is. The y-axis is mapped onto the real axis in the complex plane. So you start here, you end up here. It's a little bit more complicated than that, but that's the situation. So that's the deal with the y-axis, and that works out quite nicely. The x-axis is going to take a little bit more work, but on the x-axis, what you see is that well, on the x-axis, you have the parameter is just t. It's a real parameter, t. And so you have the w is still a fraction, and it is t minus I on top, t plus I on the bottom. And what we're immediately going to do is say, oh, we got to rationalize this. And so let's do that. We'll just multiply top and bottom by t minus I. And so I'm writing that in. And then I'm going to do the actual algebra that goes with that. On the bottom, you've got t minus I, t plus I, so that leads to t squared plus 1. Oh, that makes us breathe a sigh of relief. T squared plus 1 is always positive, never 0. We like that. Let me tell you, we really like that. Okay, and on the top, we've got, well, it's just t minus I quantity squared, so this is just math 1108 with an I toward the complex thing. So this is t squared minus 2I. Oh, you've got, it should be plus I squared, so it's minus 1. So there is the top. And now we'll separate that off into real and imaginary parts. I'm just going to write x is something and y is something. So we have that x is a fraction. It's the real part is x. T squared minus 1 on top. T squared plus 1 on the bottom. And y, the imaginary part, is a fraction. It's minus 2 on top and t squared plus 1 on the bottom. So there is where, remember, t is on the x-axis, so this is the x-coordinate for any given t. This is the y-coordinate. It's just ordinary parametric equations. Now, given the hegemony of the trigonometric functions, you probably may not have seen this. These two functions parametrize a circle. If you look, when you square x, you've got on top t squared minus 2t plus 1. When you square y, you've got, I'm sorry, I dropped a t here somewhere, so that'll make it make more sense. When you square y, that's the correct thing to say. You've got a 4t, and so what happens is you just get t squared plus 1 over t squared plus 1. So that's 1. So it's the case that x squared plus y squared is 1. So we're on the unit circle. And so what we're seeing is that the imaginary axis gets sent to the real axis, and the real axis gets sent to the unit circle. This is a general phenomenon with these fractional linear transformations. One of the big geometric properties is that circles and lines are sent to circles and lines, and that's what we're seeing here. We got some lines, and one of them gets sent to a line, one gets sent to a circle. Circles, sorry, look like this. And so that's a general property of these fractional linear transformations as illustrated by this. Okay, so now I want to do a little bit of calculus, just ordinary calculus, and it's going to come out. It'll be a little strange. It'll be easier if I can find my notes. And there we go. Okay, so we're just going to take the derivatives of x and y. Remember, we're working on the unit circle. We're expecting something interesting to happen. So x dot, I'm going to use the Newton dot notation, and now x is just an ordinary real function of an ordinary real input t. So I'm just going to use the ordinary quotient rule. And so I've got something on the bottom, t squared plus 1, and on top, you know what, this is a graduate level course. I'm not going to go through the details and say we end up with 4t. And y dot, going through just the ordinary quotient rule, comes out to be someplace over here. It looks more complicated, but we're going to fix it. It's a fraction. Top is 2t squared minus 1, and the bottom is t squared plus 1 squared. So now we're going to put on our 19th century mathematician hats and notice something very unusual that's gone on. So you can do the quotient rule on your own. What's gone on here is that x dot is it's related to y. It's y squared. Well, no. Y squared would have a 4t squared, and we've only got 4t. So x dot is y squared over t. And that is very exciting because that means that the derivative of x has the same sign as t, and so when t is positive, x dot is positive, so x is increasing. And when t is negative, x is decreasing. So this is the same sign as t. And we can play a similar trick with y dot. It doesn't quite work out to be quite so nicely. I'm going to skip the algebra because time's a consideration. But y dot comes out to be x times a fraction. And the fraction is it has 2 on top, and it has t squared plus 1 on the bottom. So when you do out this algebra, what you find is that y dot has the same sign as x. So if x is positive, then y dot is positive and y is increasing. And if x is negative, y dot is negative and y is decreasing. So that gives us the unit circle, and so I'm going to just kind of draw that in here. When t is 0, that would be, we don't want to plot a lot of points, but when t is 0, that means that we're at x is minus 1 and y is 0. And so we can see what's going on now as we go through here. So in this quadrant, t is, well, we better make sure we know what the sign of t is. So at the top here is where t is minus 1, and at the bottom is where t is 0. And t is 1. And you can see that x dot decreases down to 0. That's when t is negative, and then it increases. That's where t is positive. And so there's that corner point when t is equal to 0. So now we can just start to fill in some of the blanks and see that we're actually seeing a circle out of this. So in this in this quadrant here, what we have is that t is negative, so x is decreasing, and x is negative, so y is decreasing. So I'm just going to draw an arrow that shows what's going on there. X is decreasing and y is decreasing, bada bing. Okay. The next one to the right, we have that x is decreasing because t is still negative, and y is now the same sign as x. But now over here, x is positive, so y is increasing. And that's what we're seeing on this arc of the circle. We've got a decreasing x and an increasing y. Come around the corner here, we're still going to have a decreasing y because x is negative. And so that brings us around the corner this way. And finally, the last little bit is we've got the t is negative, so that means that x is decreasing. And why shouldn't that be increasing? Anyway, t is positive, x is increasing, and x is positive, so y is increasing. So that brings us around the circle. So what we're doing here is starting at when t is infinity, we just work our way back around the circle and then work our way back around the circle again. And these arrows are consistent with the signs of the derivative. The funky part is we're not doing a lot of algebra. We're bringing back in x and y. And the mean value theorem says all we need is the signs, and that's true. So the rest of the surprise is going to have to come a little bit later. But right now, this is what z minus I over z plus I does. It's a very interesting function with a lot of interesting geometric content.